Luminol, officially known as 5-amino-2,3-dihydrothalazine 1,4-dione, or 3-amino-thalhydrazide for short, is one of the most well-known chemiluminescent molecules for its role in forensic blood detection popularized in many television programs. The glow is the result of a series of steps shown here if you're interested. The magic happens when oxidation opens up the heterocyclic ring, causing an excited state. When the molecule returns to ground state, a photon is released. The glow given off by luminol is relatively faint and short-lived. The reaction has been studied extensively, and chemists have come up with a few ways to modify the glow. We'll start by talking about the opening shot. I have here a liter of tap water, not distilled water. That will be important in a moment. To it, I'll add 5 milliliters of 3% hydrogen peroxide. Next, I'll add 5 milliliters of this concentrated luminol solution. I'll turn the lights out before I do. The impurities in the tap water are enough to produce the reaction I just showed you. The glow is short-lived and very dim, but what did I just pour in there? A while back, I set out to make a 1% luminol solution, and then I would be able to add 5 milliliters per liter of water, and I could do large-scale demonstrations. It ended up taking 2.5 milliliters of 6 molar sodium hydroxide to get all the luminol to dissolve. As you can see, it's 6 years old now, and I never used it. That's about to change. So give it a quick stir, and then I'll add solid potassium ferrocyanide to the solution, and we should see glowing streamers as the crystals fall to the bottom of the beaker. Remember though that the luminol solution is 6 years old. The good news is that I've used old luminol solutions before. They do generally still work, albeit a little dimmer. So if you're expecting to see glowing streamers in this first example, sorry, not going to happen. In fact, nothing was detected with the naked eye either. For some reason, it was a total dud, but I did notice something interesting when I dumped this. When I poured the failed solution into the toilet, it did produce a glow on exposure to the tap water. This got me thinking about how I can modify what I have to actually produce something that might be interesting to watch. Here's the plan. Go big or go home. Well, I'm already at home, but I'll go big anyway. This is 20 liters of tap water. And here's what's going in. 100 milliliters each of 3% peroxide and 1% luminol, and an arbitrary amount of potassium ferrocyanide. It turned out to be about 12 grams. And in goes the peroxide. At this scale, it's going to be important to make sure we have even mixing. Next up, I'll add the potassium ferrocyanide. Okay, I confess. I did a few experiments off camera to come up with the one that was going to be worth filming. Adding the catalyst before the luminol made for a nicer glow. So let me get this to dissolve. I'll turn off the lights and we'll add the luminol. Okay, here we go. And it does glow, but it's dim and it decays very quickly. If you did the math, 100 milliliters of the peroxide and luminol correspond to 25 liters of water, and this is only 20 liters. Adding more tap water to this produces some nice effects. Here are a few of the better ones. To get them, I added 1 liter of tap water at a time. Sometimes hot, sometimes cold. And sometimes in strange patterns just to see what I could come up with. I experimented with the camera a little bit too. I found a good setup for taking pictures with really high exposure and extended shutter speeds, and was able to capture a few decent pictures. I ended up using all the luminol solutions, and I had a whole lot of fun doing it. The white of the toilet really brought out the glow. In case you might be wondering, normal urine doesn't make it glow. if it did glow, that would indicate blood in the urine. Normally, flushing the toilet rejuvenates the glow when fresh water comes into contact with the luminol solution, but urine quenches the glow completely. Or so I've heard. And this is what happens when you dump about 10 liters of this stuff into the bathtub with the water running. All told, I made about 50 liters of the active solution, and I have to say that the hour I spent playing with this stuff is the most fun I've had with chemistry in years. It didn't show up on the video too well, but here are a few still shots of spraying the handheld shower into the solution in the tub. Wherever the water hit where luminol solution splashed, it glowed. Some did show up on video, but it was very dim. It was definitely cool to watch, but the fact that tap water got luminol to glow is a pretty good demonstration why it's not the ideal forensic tool. Anyway, as much fun as all that was, let's do something else, starting with a 0.6% potassium ferrocyanide solution, to which I will add 10 milliliters of 3% hydrogen peroxide. See a pattern here? In a larger beaker, I'll measure out another 100 milliliters of a proprietary luminol solution. Notice how viscous it is. One of the components is hydroxyethyl cellulose, which gives it that viscosity. It helps to slow down the reaction a little bit too. We'll put that beaker onto a stirring motor and throw in a nice beefy stir bar. Let's get it stirring. Remember the potassium ferrocyanide peroxide solution? That one. I'm going to turn off the lights and then add it right into this. And there you go. Immediately you notice the glow is a different color, a bit more whitish. It also doesn't decay nearly as quickly, but it does decay quicker than it should. The proprietary solution is manufactured by a popular educational laboratory supplier as a way to have the luminol reaction last a longer time. I tried it when I bought the kit, and it did glow pretty bright for at least 10 minutes before it started to dim. The solution is now about 4 years old, so it's not as impressive as it used to be. The change in color is caused by two fluorescent dyes that are mixed into the solution. In this kind of experiment, fluorescent dyes are called sensitizers. The quick and dirty explanation is that the luminol still reaches an excited state, but rather than returning to ground state by the release of a photon, it comes down by passing on the excitement to one of these fluorescent molecules, and they in turn go back to ground state by releasing a photon at a different wavelength than luminol, which is why it appears as a different color. And the additional step in the process is why the color lasts longer. With fresher reagents and with the hydroxyethyl cellulose slowing down the molecular motion within the solution, you can see a glow for as long as 20 minutes in this particular system. So moving on, and normally you save the best for last, and normally that would be this reaction. Don't get your hopes up though. I'll run through it quick because it could be interesting with fresh reagents. The one on the far left is the key solution, and it's obviously no good. It contains luminol and sodium hydroxide, of course, and a rather nasty chemical called pyrogallol. It's pretty toxic. The solution is supposed to be this brown color, but there are chunks of who knows what all over the place, and yeah, failure in the making. Still, to 40 milliliters of this solution, I'm dissolving 25 grams of potassium carbonate. The solution is 2.5% pyrogallol, 2% sodium hydroxide, and 0.1% luminol. Once the potassium carbonate is dissolved, I'll add 10 milliliters of formaldehyde, the hardcore 37% stuff. So to recap, the brown solution is toxic, gross colored, and hasn't survived extended storage. Now add a non-trivial amount of formaldehyde so it smells bad too. Great idea. I've done this reaction before with fresh reagents and it is pretty cool. It's smelly and very messy though. So if it doesn't work, it's a horrible disappointment. And unfortunately, it doesn't work. And it's a horrible disappointment. As usual, I'll keep going anyway. Once everything's mixed up, into a 250 milliliter cylinder it goes. Ugh, delicious. So what makes this reaction awesome, when it works, is that there are actually two different chemiluminescent reactions in one. The first one gives off a bunch of oxygen and it spills over the sides of the cylinder. So I'm going to put this whole thing into a 2-liter beaker to try and catch the mess. And to be extra sure, this giant tray. And now 25 milliliters of 30% hydrogen peroxide. So while you watch nothing happen, this is what's supposed to happen. When the peroxide is added, oxygen is released in an excited state. This has a deep red glow. That part worked, but the glow was too dim even for the camera's maxed out settings. Then the luminol has a chance to get into its excited state and release its blue photon as it returns to the ground state. That part did not happen. So now I'm just left with this horrible, stinking mess that even overkill couldn't contain. Definitely use ventilation with this reaction and wear gloves whenever you're dealing with pyrogallol. The oxygen bubbles that are still forming are kind of fun to look at, but still not worth the mess. I'm still cleaning out the chemical storage room, but in the next video I'm going to be doing something a little different. I have an old bottle of iron 2 chloride that has completely oxidized except for a few little crystals that formed an oxide coating and have been protected from further loss. I'm going to try a few things to recover what's left behind. We'll see how that goes. Thanks a lot for watching, and I'll see you next time.